In the name of Almighty God, I'm Master Sankasha, and today I want to talk about piezoelectric shear actuated beam. New shear actuated smart structure beam finite element method. This simulation presents the formulation and validation of a new adaptive sandwich beam finite element capable of dealing with either extension or shear actuation mechanism. This is reached by coating an elastic core with piezoelectric sheet or sandwiching a piezoelectric core between two elastic faces. The pulling direction is taken parallel to the transversely applied electric field for the first mechanism and in the axial direction for the second one. The sandwich construction is made of unsymmetric thin faces, Euler-Bernoulli beams, and a relatively thick core or Timoshenko beam. The obtained two-node finite element has only four mechanical degrees of freedom, which are the deflection and its derivation, and the mean and relative axial displacements of the face's midplanes. Finite element analysis of segmented and continuous cantilever adaptive sandwich beams with active faces, extension actuated or core shear actuated, show good companies with results found in the literature. Additional parametric studies or actuators position are thickness, structures, stiffness, which the present element indicate that the shear actuation mechanism represents several promising features over the conventional extension actuation mechanism. In fact, the shear actuation mechanism is better than the extension one for stiff structures and thick piezoelectric actuators. Recent and current research efforts in the field of structural control using active materials are directed towards improvements of the actuation capacity of these systems. Conventional monolithic piezoelectric actuators produce longitudinal stresses or strains through their stress-induced E31 or stress-induced D31 piezoelectric constants. Their models are based on a prior assumptions of true thickness constant applied electric field and uniform pulling, and in plane constant stress or stress behavior. Using interdigitated electrodes, IDE transverse actuation through E33 or D33 piezoelectric constant can also be introduced. However, a complex pulling pattern results in the actuator due to induced in-plane component of electric field. This must be accounted for any model by sandwiching a piezoelectric layer between off-axis laminate. The composite laminate can produce twisting deformation. To transform piezoelectric constant E to the power of 36 or d to the power of 36, but this twisting is secondary since it is caused by the extension twisting coupling. This can also be achieved through special piezoelectric attachment techniques, electrode designs, or piezoelectric fiber composites (PFC) with or without interdigitated electrodes IDE-PFC. All above advanced techniques are based basically on the extension actuation mechanism of the piezoelectric materials because the electric field and pulling vectors are always parallel and the inherent shear effects of the material are always neglected. Hence, the e to the power of 15 or d to the power of 15 piezoelectric constants are not used by the above advanced actuators. To be used These require constant electric fields but perpendicular to the Pauling vector. Although mentioned early in the 19th, shear-based actuators were proposed only recently through a preliminary study with a commercial finite element analysis code and a theoretical model. A finite element method or model was also proposed by Benjdu and his colleagues and used to compare both extension and shear actuation mechanisms. These theoretical and numerical models use the stress-induced piezoelectric coupling constant e to the power of 15 of axially pulled piezoelectric layer of patched sandwich between thin elastic layers. D15-based torsional actuators were also proposed recently for the production of the large angular displacement and torque. Actuator designs and assembly methods, materials preparation, pooling procedures, test results for joint strength, and actuator output capabilities are discussed. This report and simulation pointed out the current commercially available piezoelectric or piezoceramics are not optimized for their shear piezoelectric response, and that most of the current piezoelectric or ceramics are optimized for their extension piezoelectric properties. It is the objective of the present simulation to present a new adaptive sandwich beam finite element capable of dealing with either the extension or shear actuation mechanism. New mechanical model is proposed to avoid shear locking present in the previous element. This model is based on the use of mean and relative axial displacement of the midplanes of the faces instead of those of the upper and lower skins of the core used in the previous element. An extra shear strain due to the faces sliding against the core is then induced and all quantities are expressed in terms of the faces displacements. In the following sections, theoretical and fluid element models are presented, then validated through static and free vibration analysis of various cantilevered adaptive beam configurations. Results are compared to those numerical and analytic found in the literature. Conclusions and perspectives are then formulated at the end of this simulation. Theoretical model: consider a sandwich being made of either piezoelectric surface layers and elastic core or piezoelectric core and elastic surface layers. In the first configuration, the surface layers are pulled transversely, whereas in the second one, the core is axially pulled. For both cases, a true thickness electric field is applied to each piezoelectric layer. However, elastic layers are assumed insulated. All layers are assumed perfectly bonded and in XZ plane deformation state. Bernoulli Euler theory is retained for the sandwich beam surface layers, while the core is assumed to behave as Timoshenko beam. A local frame is attached to each layer at its left and center, whereas the global one is located at the left and center of the whole beam, so that beam centroidal and elastic axis coincide with the x-axis. The length, width, and thickness of the beam are denoted by L, B, and H respectively. ABC indices indicate top, bottom, and core layer quantities, and F index is used for surface layer parameters. What about the static analysis? The segmented geometric configuration of both actuation mechanisms are presented in this simulation and this figure, with L is equal to 10 millimeters, H is equal to 60 millimeters, and T is 1 millimeters. Length and position of actuator are 10 millimeter, and DC is 15 millimeters unless stated differently. Beams are clamped at x is equal to 0 and free at xl. In order to bend the beam, voltages are applied at top and bottom surfaces of piezoelectric layers, inducing bending electric forces. Material data are those given by Sun and Zhang for the shear actuator mechanism. Voltage applied to the piezoelectric core has a value of 20 volts, and for the extension actuation mechanism, voltage applied to surface actuator are about 10 volts. As a first analysis, the deflection of both beams for the continuous case, that is, with actuators having the beam's length, was evaluated and compared to the analytical results of researchers. In order to examine the convergence of the present element, in this case for the shear actuation mechanism, there is no rigid form since the piezoelectric actuator occupies all the core layer. For both mechanisms, the deformation of the continuous actuated cantilever beam was computed by only four finite elements. Comparisons of these results to the analytical solution are presented in this simulation, indicating that finite element results for the deflection of the shear and extension actuated beam matched very well with the theoretical solution. The convergence of the element to the reference tip's displacement is shown in this simulation for the shear actuation mechanism. For the extension actuation mechanism, the finite element produced errors of less than 0.05 percent for the beam's deflection. It is clear that the present element is very precise even with low number of elements, less than 2% for two elements. Besides, uh, it converges monolithically and rapidly to the desired tip's deflection. As a second analysis, actuator's position is set varied. In each case, shear actuated beam's tip displacement induced by applied electric forces is evaluated. Actuator's length is fixed at a 10 millimeter and actuator's position is set to vary in range between 10 to 19 millimeter. Results shown in this simulation indicate that the present finite element results show very good agreement with finite element results presented by the researchers using a commercial finite element code. As expected, the actuator is more effective when close to the fixed end. As piezoelectric actuation is applied in practice to different kinds of structures, it is worthwhile to investigate the effects of structures' stiffness on the performance of the actuator. Therefore, an analysis of this effect was achieved by evaluation of beam tip displacement through piezoelectric actuation for several structures stiffness ratio. These are defined as C is equal C11 is equal to C33 for the shear actuation mechanism, and C33 is equal to C11 for the extension actuation mechanism. As it can be seen in this simulation, surface-mounted actuator is more efficient when its stiffness is greater than structure's one. Nevertheless, all-two sandwich actuators are not so efficient in this case. They preserve their effectiveness in all their range, especially in the most common structures. Actuator stiffness ratio range between 1 and 10. This is a great advantage for shear actuation mechanism since, in the contrary of extension one, its performance is preserved for stiffer structures. This figure in this simulation shows also that there is an optimal stiffness ratio range for which the shear actuation mechanism is always better than the extension one. This is the case for piezoelectric PZT5H and faces a stiffer material. The variation of beam's tip deflection which the actuator's thickness was also evaluated. It can be seen here that the shear actuation mechanism is more performant than extension one for thicker actuators, as can be expected. Therefore, for the case presented, the extension actuation mechanism is more efficient in a low range. T is bigger than and larger than 2 mm, whereas as noticed from this simulation for T is equal to 2 mm. The shear activation mechanism tends to be more efficient than the extension one. Free vibration analysis. Natural modes and frequencies were evaluated for both shear and extension actuation mechanisms. Material data are the same as presented by researchers, and geometric parameters are L is equal to 15 millimeter, H is equal to 2 millimeter, and T is equal to 0.5 millimeter, DC is 11 millimeter, and A is 20 millimeter. The first five natural frequencies are given in this parameter table for both actuation mechanisms. It is clear from this parametric that the natural frequencies of the shear actuated beam are lower than those of the extension actuation one. This can be explained by the fact that the sandwich configuration is less rigid than the extension configuration because of the presence of the foam in the core. This difference increases with frequency because the foam becomes more deformed. It can be seen that in all three bending modes, actuators deformation is lower for the shear actuation mechanism. Analytic frequencies were given only for the extension actuation mechanism because there were not any in the literature for the shear actuation mechanism. Our values for the latter mechanism are given in this parametric table for future references. A theoretical formulation and finite element implementation of a new adaptive unsymmetric sandwich beam model were presented and validated. For both extension and shear actuation mechanism, mechanically, the model is based on Bernoulli Euler assumptions in the phases and Timoshenko hypothesis, the core. Rotatory inertia effects were considered for all layers electrically. The electric potential was found to be quadratic for extension actuation mechanism, piezoelectric phases, and linear for shear actuation mechanism, piezoelectric core. Besides, the sandwich beam was supposed to be short-circuited. For example, electric potential were imposed on upper and lower faces of piezoelectric layers, and natural boundary conditions, free charge, were assumed on the remaining lateral boundaries. A first adaptive sandwich beam model was developed in previous works, and due to the presence of shear locking problems in this element, a second model with a different kinematic description was developed here. This second adaptive sandwich beam model, taking into account the extra shear due to the sliding of the faces against the core, also allowed to better understand energy dissipation capacity of the beam. Theoretical and numerical comparisons of shear and extension actuation mechanisms for statics and vibration of smart beams were presented. Present results match better with analytical results than the results of the previous element, showing better convergence characteristics. Thanks to the new kinematics description, the new adaptive beam elements didn't present shear locking problems. It was shown that the surface-mounted actuators acting through the E31 piezoelectric constant induce boundary concentrated forces and moments in the structure, whereas sandwich shear actuators acting through the E15 piezoelectric constant induce distributed moments in the structure. Therefore, we can expect less problems of actuators debonding and at its extremities for shear actuation mechanism. Comparisons between both actuation mechanisms in the static piezoelectric actuation show that only thin extension actuators are efficient. Shear actuators, in the contrary, are more effective for medium thickness range. It was also shown that a shear actuator's performance is less dependent on a structure's stiffness. Moreover, for rigid structures, shear actuation mechanism presents better performance than extension one. Vibration analysis of both actuation mechanisms was presented through evaluation of natural bending frequencies and modes. Vibration modes are equivalent in both mechanisms, and nevertheless, shear actuators are less deformed than extension ones, and natural frequencies are higher for extension actuation mechanisms. The present work is being extended to implement the sensoring capacity of the adaptive sandwich beam in order to study active control applications. The chapter of exact deflection solutions of beams with shear piezoelectric actuators. Exact deflection models of beam with N actuators of shear piezoelectric are developed analytically. To formulate the models, the first order and higher order beam theories are used. The exact solutions are obtained with the aid of the state space approach and Jordan canonical form. A case study is presented to evaluate the performance of the others previously reported models.